Thank you very much. Thanks for the invitation. I think I initially got the email that I was invited by Keith Julian. And what I'll be presenting is some work we did initially in collaboration with Keith. So he had a strong impact on this work as well. And so I'll be discussing lab experiments that depart from standard Rayleigh-Benard convection. And so I'll show you what we've been doing to achieve the diffusivity-free regime of rotating convection in the lab. And so to do that, I will first discuss non-rotating convection and how we ended up using radiative heating to achieve some diffusivity-free regimes of non-rotating convection. And then a short background on global rotation, although we've had very good introductions already, so maybe this can be quick. And then I'll combine radiative convection with rapid rotation to study the diffusivity-free regime of rotating convection, which is usually called the geostrophic turbulence regime in this context. Then I'll further characterize the geostrophic turbulence regime beyond just pure heat transport, discussing the flow velocity, the length scale, etc., all the other scaling predictions. Okay, so I have a standard introductory slide on convection. Just like Adrian, I'm not going to go through it because my pictures are not as pretty as Adrian's. But basically, you have convection pretty much everywhere, right? It's the way nature moves fluids around. That's how Charlie Doring would put it. Okay, so you have convection in planetary interiors, in the atmosphere, inside stars, either at the periphery or throughout the entire star, or in the core region, and in the downward branches of the meridional overturning circulation in the ocean. Okay, but when you're a physicist, and I come from the fluid physics community, I try to come up with the simplest setup, right? So that would be Rayleigh-Benard convection, non-rotating, maybe infinite layer, until you try to set up an experiment. And so, yeah, we'll be wondering maybe about the heat transport as a function of the temperature difference driving the system. And so in dimensionless form, the Nusselt number is a function of the Rayleigh number and the Prandtl number. Okay, and the goal is to determine a scaling law, maybe using lab experiments in DNS that we can extrapolate to the extreme parameter regimes of natural systems, as we've seen. Okay, so I'll go through the theory for these exponents, gamma and chi, for non-rotating convection, which we haven't seen so far because we focused on rotating convection. So there are two main competing predictions. The first one tells you that gamma, this exponent, will be a third here. And this is known as the classical regime due to Malkus and Priestley, both in 1954, although Howard in 62 or 63 was also instrumental. And so the idea is that, yeah, sure, you'll have fully turbulent flow in the bulk. It will be very efficient at transporting heat. It will homogenize the temperature field. However, near the boundaries here, you have hardly any fluid motion, so it will be difficult to transport the heat. And you have to diffuse the heat across the boundary layers before it can be efficiently transported in the bulk. And so this will be the process that restricts the overall heat transport throughout the entire layer. Okay, so once you've understood this, you need a prediction for the thickness of this boundary layer. And the idea is that those boundary layers, they're marginally stable, meaning that if you build the Rayleigh number on the height, on the thickness of the boundary layer, you should get something that's comparable to the critical Rayleigh number for the emergence of thermal convection. Okay, that gives you a thickness delta that's independent of the height of the layer. So if heat transport is restricted by a process that does not involve the height h of the layer, P should be independent of h. So if you look for an exponent gamma such that you can cross out h from both sides of the relation, you realize that gamma should be a third, okay? And no dependence in Prandtl number here. So that all makes sense, but there's another equally convincing prediction maybe, which is due to Spiegel and Kreiknan, maybe, if you're willing to allow for log corrections. And it's based on the zeroth law of turbulence or anomalous dissipation. And you just say, well, as for any turbulent flow, the large-scale quantities should be related in a way that do not involve the tiny molecular diffusivities, right? So diffusivity-free regime. And if you demand that P and delta T be related in a way that does not involve kappa nor nu, you get that Nusselt should go like Rayleigh to the 1/2, Prandtl to the 1/2. Okay, so depending on the community, I think in the astrophysics community, this is known as the mixing length scaling regime. In the physics community, This is sometimes called the ultimate scaling regime. I tend to call that the diffusivity-free scaling regime, but that's all the same thing. Okay, now data. This is a highly controversial issue you may be aware of. And so typically the exponents that you get from lab experiments range between 0.31 and 0.38, actually high Rayleigh numbers with different experiments leading to different exponents. Bob showed us some very beautiful data set that leads to nozzle close going like Rayleigh to a third up to extremely high Rayleigh number. But I'm only going to argue here that none of that is close to 0.5. Okay, so Rayleigh-Bénard doesn't look like a good setup to observe a clean gamma equals 1/2 diffusivity-free regime. Okay? So, and also if you think about it, for many natural flows, it's unclear why you should really care about the Rayleigh-Bénard boundary layers, right? So we've mentioned stars already. It's very unclear what the boundaries would be, whether you would have the same boundary layers, etc. Depending on the mass of the star, you can have a direct overlap between the thermonuclear reactions heating up the fluid and the bulk turbulent flow. So no boundary layers here. This other example here, that's a frozen lake in the spring. So you have a layer of ice on the water. And in the spring, solar radiation penetrates through the ice and is going to be absorbed within the first meters of water here. And because this is fresh water below 4 Celsius, if you heat up the water, it becomes denser. So that's going to drive convection here. And again, the radiative heating heats up the fluid within the first few meters beyond the boundary layers. And so you don't quite see why the boundary layer would be relevant in this context. Okay, so we thought, well, maybe we could design a lab experiment where we heat the fluid radiatively, bypassing the boundary layers, and maybe that would be one way to observe the diffusivity-free regime in the lab. Okay, so that's the lab experiment. It's really quite simple. In fact, there's a tank here with a transparent bottom plate. Again, there's a powerful spotlight shining at the tank from below. It's a really powerful spotlight. And inside the tank, there's a mixture of water and dye. Again, the dye is going to absorb the light, and that's going to heat up the fluid. What's interesting is that depending on the concentration of the dye, you can tune the thickness L over which the light will be absorbed and the internal heating will take place. Okay, so we'll be considering basically 2 limiting situations. Yeah, if there's a lot of dye in here, then L is really tiny. So the heating will take place very close to the bottom boundary, inside the boundary layer, and you still need to diffuse that heat across the boundary layer to reach the bulk. So you're in a regime where the boundary layer is going to throttle the heat flux. You expect to see something that's similar to standard Rayleigh-Bénard convection. Right, and now more interestingly, if there's less dye, if we put less dye in the system, then L is going to be greater, right? And so the light will be absorbed within a significant fraction of the interior here. We're bypassing the boundary layer, inputting the heat directly into the bulk turbulent flow, and we may hope to see something that's diffusivity-free.
So just a technical question. It looks like you're screening thermal. You're also screening IR. So what part of the spectrum are you heating with? If not IR, where are you trying to, in the spectrum, to heat the water?
We are heating with visible light, is what we're doing. So it's just visible light. So indeed, so it looks easy. It's a bit tricky to build. First of all, this is really powerful spotlight. So this is kind of the spotlight that's on top of the Eiffel Tower. Think to it. Very French. Okay,
how many kilowatts? How many kilowatts is that?
It's 2.5 kilowatts. Okay, so it's quite, So it gets really hot, right? And it gets really hot, emits a ton of infrared. So if you don't filter out this infrared radiation, well, yes, it's going to be absorbed by the tank, but it's going to be absorbed over a micron or something like that, which is not what we want to do. That would be boundary heating. So instead, we want to get rid of the infrared. And one way to get rid of the infrared is to have a first layer of water that's going to absorb the infrared, but it's going to cool, to heat up so strongly that you need to water cool this cooled water. We're doing that too. We're also water cooling this screen here, this shield. And then we have pure visible light here. And there's dye, it's just carbon black dye that absorbs in the visible spectrum just with a constant rate. Okay. So I've said that. So basically, just the structure of this heating term is going to decrease exponentially with height. Okay, Z measured from the bottom of the tank. That's Berlambert's law over a height L. And so the heat source that will be in the temperature equation is P over L times this exponential, P being the total heat flux that's provided by the spotlight. And there's a 1 over L, so that if I integrate from 0 to infinity upwards, I should get the total P. Okay? What about cooling? So I've told you how I'm going to heat up the fluid. I haven't told you how I'm going to cool it down. That's because that can be an issue. If there's a cool plate at the top, then this cool plate is going to induce a boundary layer, and we'll be back to a Rayleigh-Bénard-like situation where this boundary layer at the cooling plate will throttle the heat flux. So instead, what we decided to do is to not cool down the fluid. Okay, now I'm going to show you that if you don't cool down the fluid, you end up in a situation which is similar to a system that's driven by radiative heating and cooled at a uniform and opposite rate throughout the tank. Okay, so how do you see that? You start from the temperature equation, right? Convection, diffusion, and then there is this heat source here, P over L e to the minus Z over L, that's radiative heating, and you assume that all the boundaries are insulated, and you just spatially average, okay? So that's spatial average, no time average, okay? And so you get that the time derivative of the spatially average temperature in the tank is just proportional to P, all right? The heat flux provided by the spotlight. So I'm saying something really simple here. If I'm providing heat at a constant rate to an insulated body of fluid, then the mean temperature inside this fluid is going to rise at a linear rate proportional to P, right? But now I can introduce a new variable, theta, which is the temperature field minus the spatially average temperature, okay? If I write down the equation for theta, I get the standard convection diffusion equation with the radiative heat source here, and now a uniform cooling term which balances this one over space average. Okay, and any temperature difference delta T between 2 points in the tank is also equal to delta theta because this one will cancel out. Okay, so effectively, because of secular heating, I have radiative heating and effective uniform cooling in the system. How does this work practically? Well, here's the tank. We use 2 probes, one at the bottom, one at mid-height here. And you can see here, once we turn on the spotlight, what the time series look like. So you can see the 2 temperatures as a function of time. You can see the rise pretty much linearly as a function of time. This is this drift of the spatially average temperature. And provided you're around room temperature, which was 24 Celsius in that case, you can see the 2 lines are nicely parallel, which means that the temperature drop between the 2 probes is statistically steady now. Okay, so from that portion of the signal that's around room temperature, from the slope here, you get the power transmitted to the fluid, which you also know from the spotlight. And from the difference between the 2 temperature signals, you average in that region the difference, and you get delta T. Okay, so you can form the Nusselt number and the Rayleigh number. Okay, so here is Nusselt versus Rayleigh. This first data set corresponds to a lot of dye in the tank, a Rayleigh-Bénard-like case where L is really tiny, this absorption length. So we're inputting the heat into the boundary layer. You can see Nusselt as a function of Rayleigh. The data points show nice Paolo behavior, and the best fit exponent is 0.31, pretty close to what you would get in a Rayleigh-Bénard experiment. Right, and now more interestingly, there's less dye in the tank. Okay, so now we get these data points, and also a Paolo, but now the best fit exponent is 0.54, pretty close to the prediction 1/2 of the diffusivity-free scaling regime. Okay, so indeed we can bypass the boundary layers with radiative heating and observe this diffusivity-free regime. At the time, it was a new setup, so we confirmed that using numerical simulations. Those were performed using Daedalus, and we got exponents that were pretty close to what we measured experimentally in the DNS. There's a slight change in prefactor. Honestly, I don't quite know why. Maybe because the experimental tank is a cylinder and these DNS are in cubic geometry. Could be. Okay, so that's the end of this first part on how we ended up using radiative heating to observe diffusivity-free. Yeah.
Since you're doing radiative heating over some distance, then that adds some uncertainty to the definition of the heat transport, right? Because where do what is H? And you said it was like 5% or something of the total?
Yes.
So both the Rayleigh number and the Nusselt number are, there's some uncertainty exactly in how you define the height, and that leads to some systematic uncertainty in your data points. Yes? No?
I mean, you're right that there's indeed these L that's fixed. I don't think it's an uncertainty. It's just a new control parameter, which is L over H, and you can determine the dependence on that parameter. So for instance, here, nu and Rayleigh are based on H, because this is what you would do in the limiting Rayleigh-Benard case where L goes to 0. What you can do, for instance, is then Vincent Bouillot ran a lot of those experiments beyond this example, where he varied systematically the L over H. And you can see that in this ultimate regime, in fact, Nusselt is proportional to Rayleigh to the 1/2, Prandtl to the 1/2, but also L over H. Okay, so you can determine that scaling dependence in L over H. Okay? But, I mean, you're right, the geometry involves a new length scale here, which you can vary. To be fair, in any natural system, there's probably, in a star, what would you do if you have internal heating? Yeah. Yes?
As you change the absorption length, is
Yes.
the transition smooth between the two scalings, or do you have a threshold where it switches from one to
Yeah, very good question. I wish I had a backup slide for that. The transition is pretty sharp. So, yeah, for some values, we're just seeing a nice close to 1/3 exponent, and at some point, it transitions to 1/2. Basically, this is not exactly what it is, but pretty much you expect the transition when this L becomes greater than the bandular thickness, right? So that's where the transition should be. So very low L, you're going to get data that show 1/3, right? Until you're at high enough Rayleigh number that the bandular thickness becomes less than L, and then you should transition to 1/2, okay? So the transition is sharp.
There could be some kind of feedback mechanism that makes it sharp.
Sure, yeah. Yeah, because then you're in a different regime and maybe the bandular is set through a different mechanism. Yes. Mm-hmm. Yes.
How good is the estimate as exponential minus z over L with a single L when you have a large spectrum in your light?
Yeah. Well, that's something you have to measure and check. So we check that it's pretty good. I don't know. I don't have the data. It's pretty good. So we're using carbon black dye, okay, India ink. Okay. And so it's pretty good because it's just these, black dye that's just blocking any wavelength. So one way to do it is like you fill up the tank gradually and use a flux meter, and you can see as a function of the height of fluid. So we've measured that, and yeah.
Since your sketch was blue, I was wondering the dye was blue.
Oh, in the sketch, was it blue? No, it's pitch.
It's dark.
Yeah. Yeah. The sink is black. Yeah. Okay. So now, impact of global rotation on a convective flow, right? Rotating Rayleigh-Benard convection. We've had great talks on the topic. So now there's rotation, an additional dimensional parameter. So there's an additional dimensionless parameter. Typically, you could use the Ekman number. And our Nusselt should be a function of Rayleigh, Prandtl, and Ekman. And that makes dimensional analysis challenging because the reasoning I've shown you before for non-rotating convection will not be sufficient to just close and determine the 3 exponents just based on the diffusivity-free assumption, say. So you have to say something more. And as we know, you can make progress by considering the asymptotic regime of rapid rotation. Okay, so we've seen that rotation suppresses convection, so it delays the threshold, which now scales as Ekman to the minus 4/3. And if you do the full linear stability analysis, it comes with scaling laws for the dependence of the horizontal scale, the vertical scale, the temperature fluctuations, or the ratio of the temperature over velocity ratio. This is all encoded in the structure of the eigenmode of the linear stability problem. Okay, and so I'm going to come back to that, but part of the idea is that these scaling dependence in Ekman, they're going to remain valid at finite supercriticality as Ekman is sent to 0. Right? So this is the reasoning behind the expansion by Keith Julian and Edgar Knobloch. So they performed an expansion in powers of Ekman to the 1/3, assuming that the supercriticality Rayleigh over Rayleigh C is kept constant. Okay, so it's order 0 in Ekman number. So the crucial point when they do that is that they get this reduced set of equations that only involve the reduced Rayleigh number, Rayleigh Ekman to the 4/3, which is a measure of Rayleigh over critical Rayleigh up to a multiplicative factor. And so now, instead of saying that the Nusselt number is a function of Rayleigh, Ekman, and Prandtl independently, you just have these two parameters, reduced Rayleigh number and Prandtl. And now if you use the diffusivity-free arguments, because you have only two control parameters here, you'll be able to conclude on the full scaling behavior of the Nusselt number. Right, so you can do two things now that you know that Nusselt is a function of Rayleigh, tilde, and Prandtl. You can use boundary layer arguments similar to the classical regime of rotating convection. Okay, so you'll say that the transport is restricted by marginally stable boundary layers, but now marginally stable according to the stability limit of rotating convection. And you get that Nusselt goes like Rayleigh cubed Ekman to the 4. But you should be careful maybe of Ekman layers that could kind of disrupt this argument. But I'll be focusing more on bulk control, where you say, again, use the diffusivity-free assumption. Okay, these should depend in a parallel fashion on the reduced Rayleigh number and the Prandtl number in such a way that nu and kappa can be crossed out from both sides. And that leads to the Nusselt number going like Rayleigh to the 3/2, Ekman squared Prandtl to the 1/2. And so this is known as the geostrophic turbulence scaling regime, and this is basically the diffusivity-free regime of rapidly rotating convection. Okay, so there's some good news in here, which is that as compared to non-rotating convection, we know that asymptotically, because this is less steep than this one, the bulk should be the throttle for rapidly rotating convection asymptotically. Again, the boundary layers should be very efficient at transporting heat, and this is what should restrict the overall flux. But you have to reach the asymptotic regime, and so I'm also using this great schematic from Cheng et al. 2015, okay, where you have to perform ever taller rotating Rayleigh-Benard cells, and there's this amazing 4-meter high experiment, okay, where we try to achieve this asymptotic regime. Okay, so what are typical observations? I don't know if they're...
Wow, that's John Chang.
This one is not Cheng, yeah? This is that's not...
John Chang.
It's not King and Ornu?
It is, yeah.
Oh, it's,
Johnny Chang.
okay,
All
I'm
good,
sorry.
all good. Sorry, no, I mean,
Sorry about that. Okay. So now data, not only schematics, and so yeah. So you can see the Nusselt number, the function of the Rayleigh number, right? And the colors are different values of the Ekman number. Okay, and there's some lab data, and I think the open symbols are DNS. And basically, what you see, typical ideal example is this. Those pink symbols here. So you can see that convection is delayed because of rapid rotation, but eventually you hit the onset here. Then you have a very sharp increase, something like Rayleigh cubed. Okay, so maybe boundary layer control of rotating convection. And very quickly, you reach this asymptote here, where now Nusselt goes like Rayleigh to the 1/3. This is the non-rotating regime. Okay, now the flow is fast enough that the Rossby number is large enough and the system doesn't feel rotation anymore. It's back to non-rotating Rayleigh-Benard convection. Okay, so basically it seems to go from boundary layer control to boundary layer control, and we don't see the geostrophic turbulence regime in this data set. Okay, so we thought, well, maybe, radiative heating, again, would be a good way to bypass the boundary layers of this regime. So we adapted the experiment, which is now rotating. It's fairly easy because you don't even need the rotating table because of these remote way of heating up the fluid. So we just attach the tank from above to a motor that's spinning at a constant rate, and then we're making temperature measurements in the rotating frame and sending the data through Wi-Fi to a remote computer. Okay. So qualitatively, here is some information we can get on the flow. Once again, it's very dark. So we cannot do PIV or anything. What we're doing is, because we have a top free surface, we can image the free surface using a thermal camera. Okay, so you're looking at the temperature field at the surface. And so without rotation, you can think of the flow as this large-scale convection roll, where some warm fluid is going to impinge on one side of the surface, that's here, and some cooler fluid is going to fall down here. So you can see this video. Okay, so it's reasonably turbulent. And now when there's rotation, we know that the horizontal length scale should be smaller, and you can see these small convective plumes here. And if I play that movie, this is what this flow looks like as seen from above in terms of a temperature field. Okay?
So can I ask a question? So you don't have anything capping the top of the tank. So why don't you have some heat loss out the top?
There's going to be heat losses eventually once you're, away from room temperature.
But you equilibrate and have this long steady state.
Yes, well,
long
if you
enough.
look at those lines, they're nicely parallel, I guess, between plus and minus 3 Celsius of room
And,
temperature,
and the
maybe
key is
4
you're roughly
Celsius.
starting a little below and ending
Yeah,
a little above.
so we
room
fill
temperature.
the fluid with really cool water, something like 5 Celsius. Okay, and then all the transient is during the warming phase, and then once it's around room temperature, it's in a nice statistically steady state. But yes, you have to start, especially with rotation, because the transient can be pretty long, so you have to start with really cool water. Yeah.
So you're heating up the water. How much of a height change do you have over one of these runs until things getting hotter and hotter?
Sorry, say again. How much?
You've got a free top, and you're heating up the column.
Yes.
Presumably, the mean density of the water is changing. How much
Oh.
change of height is that?
It's tiny. I mean, yeah, the thermal expansion of water is 210 to the minus 4. So 10 Celsius would be, 0.2%? Then in terms of change in density, so it's really, it's all very Boossian-esque. Yeah. Okay, so now quantitatively, so what I'm going to do is, in this experiment, what's really imposed is the heat flux, and we're measuring the temperature drop. Okay, so usually convection, standard Rayleigh-Benard convection is fixed temperature, and you measure the flux. But as in electronics, maybe, where you can fix the voltage, measure the current, or fix the current, measure the voltage. Here we're fixing the flux and measuring the temperature drop. Okay, so because the heat flux is imposed, the control parameter is the dimensionless heat flux, okay, alpha GPH4 over lambda kappa nu. So that's the flux-based Rayleigh number, and it's just the product of Nusselt times the standard temperature-based Rayleigh number. And we measure delta T to access Nusselt and Rayleigh if we want. Okay, so you can recast the geostrophic turbulence scaling law for the Nusselt number in terms of Rayleigh P, right? You just substitute Rayleigh equals Rayleigh P over Nusselt in the previous scaling law, and you get that Nusselt goes like Rayleigh P to the 3/5. Okay?
Sorry, so Nusselt is like the inverse temperature difference now?
Yes. Yeah.
So actually, could I go back? So did you measure, was it P you were measuring through the drift?
You can measure P,
temperature?
yes.
Was that the better measurement than delta T? Like, why did you choose, was there a good experimental reason to go to flux-based Rayleigh? Because it looks like you had nice Rayleigh numbers. Why not fit a 3/2 law?
Yeah. Yeah.
It doesn't
we could,
matter.
but at some point,
They're one and the same.
I think it's because at some point, we're trying to just make contact with the Rayleigh-Benard literature in the first non-rotating paper. But at some point, this is what the experiment is like, and the flux is fixed. So, but we could do the conversion and produce the figure. Maybe it's a supplementary material or something. Yeah. Okay. Right. So now this is what the raw data looks like. Some of the data. This is Nusselt as a function of Ekman number. So rotation increases from right to left. These data points correspond roughly to a constant flux-based Rayleigh number. Not exactly, because they were not performed exactly at the same temperature. But what you can see is that for a given flux-based Rayleigh number, as you increase rotation, indeed, you're going to suppress convection. And now you can ask, well, is that diffusivity-free convection? How would I know from this plot? And so one way to check whether this is diffusivity-free is to introduce control parameters that do not involve the diffusivities anymore. Okay, so you can combine the flux-based Rayleigh number with Ekman and Prandtl in such a way that you will remove nu and kappa. In fact, you get this diffusivity-free flux-based Rayleigh number, R, which ends up being related to a flux-based convective Rossby number, which would be R to the 1/5. Okay, but basically you can make it independent of nu and kappa. And then all the emergent quantities of interest, and I'll be focusing on the Nusselt number for now, can also be made diffusivity-free. So you multiply the Nusselt number by Ekman, you divide by Prandtl, and you get a measure of flux over delta T, which does not involve nu nor kappa. Okay? And all the geostrophic turbulence predictions, they look like the diffusivity-free form of your order parameter is some function of your diffusivity-free control parameter, so some parallel of R. Okay, and so this 3/5 that we got in terms of Rayleigh flux, it just becomes that this Nusselt star is R to the 3/5. Okay, so I'm going to show you the data in this plane R Nusselt star, diffusivity-free Nusselt number. So the first question we ask is the system indeed in a diffusivity-free parameter? If that's the case, all the data should collapse onto a master curve, right? And then is this diffusivity-free regime the GT regime? If that's the case, the parallel should be with a 3/2 exponent. Okay, 3/5 exponent, sorry. So that's the data. The triangles are numeric, so just look at the circles for now. So the first thing to notice is that indeed the data set collapses onto a master curve. So it's a diffusivity-free regime of convection. This part here is the non-rotating regime. So here rotation is too weak to impact the system. And you get that Nusselt star goes like R to the 1/3. This is the ultimate regime of non-rotating convection. But surprisingly enough, in terms of the flux, it becomes an exponent 1/3, which is very confusing. But that's diffusivity-free non-rotating convection. And more interestingly, as you increase rotation, so that's going to the left on this diagram here, you get to this different parallel behavior here, where Nusselt, diffusivity-free Nusselt numbers goes like R to the 3/5 here, which is a good indication of the experimental observation of the geostrophic turbulence scaling regime. Okay? So that's for the flux. We were quite happy about that, but we also wanted, okay, so sorry, some DNS here, and now we use the code Coral by Ben Mikkel that Adrian is also using, and we got these points here, these triangles. I think that's for a different value of the absorption length. Yeah, sorry, that's what I had here. So now let's try to characterize this regime further to try to see if it's indeed the geostrophic turbulence regime. So let's see. Like I said, there are other predictions here. So if you're interested in the temperature fluctuations, which in the geostrophic turbulence regime scale in a different fashion than the overall temperature drop, you can build a Rayleigh number based on the root mean square local temperature fluctuations. You can build a diffusivity-free Rayleigh number based on the fluctuation. And this diffusivity-free Rayleigh number will go like R to the 3/5. Okay? You can measure the root mean square velocity in the system. That would be in the numerical simulations, because we're going to have to turn to numerical simulations. You can build a Reynolds number. You can build a diffusivity-free version of this Reynolds number and study that. It should go like R to the 2/5, according to the theory. You can measure the horizontal scale and see how it depends, again, on R. It should be R to the 1/5. Maybe I can explain how we get these laws here, because it's related to this question of the viscous length scale versus diffusivity-free length scale. So in fact, there are nice shortcuts to get all these scaling predictions, which is that basically, let's look at this horizontal scale. So our perpendicular of h, a priori you'd say, well, it's some function of Rayleigh, Prandtl, and Ekman. Okay, but you would say, maybe Keith would say, well, maybe it's, you should write it maybe as a function. F is any generic function. It changes from one line to the next. Maybe some function of Rayleigh, Ekman to the 4/3, Prandtl, and Ekman. Why not? At this stage, it's the exact same thing. And then you would say, well, if you send Ekman to 0 for fixed Rayleigh tilde, then surely it will be some parallel Ekman to the alpha, and then some function of Rayleigh tilde, okay, which is this Rayleigh Ekman to the 4/3 and Prandtl. And then you can say, well, but at this stage I don't know alpha, but there's one thing I know how to do. It's linear stability analysis. Okay, so I know that if when Rayleigh tilde is very close to critical, so it's not exactly 1, but say it's approximately 1, then I'm close to threshold. Linear stability tells me that alpha is equal to a third. And that's because I can read, right? And I've read Chandrasekhar's book, maybe. That's linear stability. So now, I've learned a lot. I know that L perpendicular over H. And you see, I don't have to do anything but read the linear stability analysis. I think that's really cool. And then I have Rayleigh tilde here and Prandtl. Okay, so in connection with this morning's talk, yes, it will have this viscous control Ekman to the 1/3. But now you can invoke the diffusivity-free argument. If you say, well, okay, Ekman is going to 0. It's so small that even Rayleigh tilde equals 10, 100, or 1,000 is Ekman to the 0, then Rayleigh tilde can be large enough that I can say, well, maybe I will reach a diffusivity-free regime. Meaning that now I'm going to assume exponents here, where L perpendicular over H is Ekman to the 1/3, Rayleigh tilde to the beta, Prandtl to the gamma. And then I'm going to look for exponents that cancel the dependence on nu and kappa on the right-hand side, right? So I can look for powers of nu. On the left-hand side, I have 0. On the right-hand side, I have 1/3. Then Rayleigh tilde is Rayleigh Ekman to the 4/3, so it has nu to the 1/3 plus beta over 3. And Prandtl has nu upstairs, so it should be something like that. And then powers of kappa, you have 0 on the left-hand side. That should be equal to the power of kappa on the right-hand side. That's 0 here. That's minus beta here and minus gamma here. Okay, let's hope this is correct. So gamma is minus beta, and I get that 2/3 of beta equals 1/3. So beta would be 1/2, and gamma would be minus 1/2. Okay? So this would mean that L perpendicular over H is Ekman to the 1/3, Rayleigh tilde to the 1/2, Prandtl to the minus 1/2. And now if you substitute, you may want to substitute the expression of the reduced Rayleigh number, and you get that L perpendicular over H is Rayleigh to the 1/2, Ekman to the 2/3 plus 1/3. That's Ekman to the 1, Prandtl to the minus 1/2. Okay, and I hope. Okay, and maybe to make the connection between the two scalings, yes, you'd say because of linear stability, what I know about linear stability, it has to go like Ekman to the 1/3. But now there's also this factor that involves nu in here and in here. And if I want it to be diffusivity-free, I will pick these powers such that nu and kappa can be crossed out, and you get these scalings. Okay? And in terms of the flux-based Rayleigh number, diffusivity-free, that translates into that relation. Okay? I just think it's a nice shortcut, but I don't know. All right, I don't know how much time I have, but I'm nearly done. So we turn to 3D direct numerical simulations using Coral again, using some of the DNS. We try to cover the range of parameters of the experiment. So here, experiments or circles and DNS are triangles in here. So first we can look at the heat transport to check the consistency between the DNS and the experiments. The experiments are done using periodic boundary conditions in the horizontal. So it's also one way to check whether we get a strong impact from the boundaries, and this from the lateral boundaries in the system. Okay, the prediction again is nu star goes like R to the 3/5 for the geostrophic turbulence regime. So that's basically the same. Oh, there should be a nu star here. Apologies. This is basically the same plot as before, but now you also have the triangles here that are nicely superposed with the experimental data. So that's all consistent, and we can now go to study other quantities. These are temperature fluctuations. So again, you can build a diffusivity-free Rayleigh number based on the temperature fluctuations. this should go like r to the 3/5. Okay, and again, we have the experimental data here, that's the circles, and the DNS are here. A slightly larger prefactor for the experimental data, I'm not quite sure why, but in both cases, we get a good agreement with the power law 3/5 again for this quantity. Velocity scaling, so the diffusivity-free Reynolds number is Reynolds times Ekman, okay, which is also known as, you see, I've been careful not to not see, okay. Yeah. This is also the emergent Rossby number, right? But yeah, okay. That's the emergent Rossby number, which goes like r to the 2/5. Okay, so we can check that. This is here, this emergent Rossby number. So indeed, it goes like r to the 2/5. This 1/3 would be the prediction without global rotation. So indeed, we're in the rapidly rotating regime, where we're seeing 2/5 here. And we can look at the length scale, which is defined in our case as an integral length scale, which we built using the toroidal stream function in the system. So psi is the inverse Laplacian of the vertical vorticity, right? So from psi RMS and URMS, you can build this integral length scale. And this is an integral scale, so it should go like r to the 1/5. I should also say, if you want your length scale to be diffusivity-free, you should look at a large length scale to invoke the zeroth law of turbulence and not a Kolmogorov scale, for instance, obviously, which will involve the end of the turbulent cascade. Okay, so again, yeah, here we get a pretty good agreement with the r to the 1/5 here for this horizontal length scale. So yeah, I think we can validate pretty much all the predictions of this geostrophic turbulence regime in the system. So that's the summary. You can combine radiative heating with rapid rotation to observe diffusivity-free rotating convection in the lab. And I'm going to stop here, maybe just a few slides of perspectives or questions. I felt bad because, basically all these talks have been about avoiding the boundaries. And so maybe, question I ask, Rudy asked me why I don't have much of a signature of the wall modes in the experiment. And that's a fair question. Maybe it's because we're measuring at the center, but I also think there should be something else, which is that we're fixing the flux in the end, like a flux that's uniformly distributed over the horizontal. Okay, and I think that could be maybe, I don't know, I'm asking, so if anyone's interested, we could investigate this. The standard setup seems to be fixed temperature rotating Rayleigh-Benard convection. In which case, if you have wall modes, then they seem to be very efficient at transporting heat. So it means you have a very low thermal resistance here and a higher thermal resistance here. So of course, if you impose a constant temperature difference, you're going to have a huge flux here in the wall regions and a weaker flux in the bulk. It's again, if it's electronics, you have a small resistor here and a large resistor here, and they're all in parallel. Well, most of the currents is going to go through the small resistors, right? But instead, if you fix the flux, that cannot happen because you're imposing the flux everywhere on the surface. So there's no way this is going to transport a lot of heat because you're just not supplying that much heat here in the wall layers. Okay, and so I'm wondering, could it be that fixed flux, it's tricky to do in the lab, but it's feasible to approach the fixed flux boundary condition. Wouldn't that be maybe even a simpler way than the fins suggested by Terrien et al. To just have little flux through the wall modes? Maybe they won't be as energetic, and would you see convection controlled by the bulk only? So that's something we could test in DNS. So that the flux would be maybe more uniform. It would be easy to test using DNS in a cylinder, maybe. So I'd be interested in doing that, and even more in trying that in a lab experiment. So if anyone is interested in trying to build a fixed flux boundary condition, you just need one, I guess, not two. That should be sufficient. It's tricky to do, but I think it's worth giving it a try. Maybe that could work. So that's one question I have, at least, to get rid, just mitigate the influence of the wall modes. One last question I had, different thing, was the opposite direction. You embrace the wall modes. And one question I had is there a diffusivity-free regime of wall mode convection? Okay, so I've borrowed this schematic from Basile et al. It's not even out that I'm already stealing the pictures. But we've seen this parameter space, right? This is Ekman to the -2 Taylor number. We've discussed this triangle where the wall modes exist. And so at least theoretically, you can think of what happens in this region where you're so far, at such low Ekman number, then you can have only wall mode convection, but far away from threshold that it should be diffusivity-free, or maybe. What would be the scaling predictions? Can these be observed? Well, I think we don't know at this stage. And maybe a good starting point for that would be to start with the reduced model that is in this paper here, which is a way to maybe isolate this form of convection and see whether it ever becomes diffusivity-free. Okay, so 2 topics I'd be happy to work on if anyone's interested. All right, I'm going to stop here. I thank my collaborators. So the lab experiments was modified by Vincent to add global rotation, perform the heat flux measurements, then Gabriel performed some further measurements and the DNS and processed the DNS. Benjamin Michael wrote the code Coral. Keith Julian helped us at the theoretical level quite a lot. And Sébastien Maître is a very good experimentalist and colleague of mine at CEA Saclay. All right, thank you very much.